We now know how to write a null and alternative hypothesis. What we want to be able to do now is to understand how we make a conclusion. Now there's a lot of things that are already written down for us, so let's go through what's written down and how we use the critical value approach, how we compare a critical value and a rejection region to a test statistic. So I have three examples here. I have my first null and alternative hypothesis set. I am looking at a null always having an equal to, and I'm looking at mu, in this case the population mean, being greater than. In the last video we saw greater than is associated with a right-tailed test. In the middle we have a left-tailed test because our alternative is less than, left less, left less. So we have a left-tailed test. And over here on the right-hand side we have not equal to. So we have two areas here to both sides. This is a two-tailed test. The basics of the critical value approach. What we're going to do is we're going to, when we're using the critical value approach, we're going to label our bell curve. So we'll draw our bell curve. The population parameter in question here, if we look at our first example, is 2, so that would be in the middle of our sampling distribution. And then we're testing that against the claim that the population is actually, in this case, greater than 2. So how do we know which is true? How do we know which has more evidence for it? The null, that it's actually just equal to, there's no change, or the alternative, where there's actually evidence to support that it is greater than 2? Well, that's where the critical value comes in. The critical value is going to be a z-score if we're talking about a population proportion, or a t-score if we're talking about a mean, that separates what's called the rejection region from the fail to reject region. Now, the critical value, let's say in this example that we wanted to have a level of significance of 0.05. So let's say we wanted to have a level of significance of 0.05. That means we want, in our rejection region, we want the probability or the area of our rejection region, in this case, this area here to the right of the mean, to be 0.05. So what we're going to do is to find the critical value, in this case it'll be a t-score, find the critical value that has 0.05 with a certain number of degrees of freedom to its right. If we calculate, let's say we calculate our sample, and our sample is, let's say 3.2. Right? We're looking, our mean here, we're testing whether or not the population is greater than 2 or equal to 2, the mean. We get 3.2. How do we know if that's significant or not? Well, we're going to calculate a t-score. We're going to calculate what's called a test statistic. Test statistic associated with 3.2. In other words, how far from the sampling mean here, the sampling distribution mean, is 3.2. If 3.2, the test statistic, lies in the rejection region, then we're going to reject the null in favor of the alternative. So again, we look to see whether or not our test statistic lies in the rejection region. In the second example here, we see that this is a left-tailed test, so the rejection region is to the left. If we find a, let's say we find a test statistic that lies not in the rejection region, but actually lies before it. It's not in that rejection region. It's not past that critical value. Then we will fail to reject. So our options are either reject the null or fail to reject. And then finally, in this particular case, we have a two-tailed test where we actually have two rejection regions. And instead of having alpha, the significance level, being all in one tail or the other, we actually split it in half and put half in one tail and half in the other, similar to what we did with confidence intervals. So let's look at a quick example. We are testing the claim that the mean pulse rates for men is more than 74. We take a sample of 30 men to find a mean of 78 and a standard deviation of 3.2. We're going to use a level of significance of 0.05. Let's first write the null and alternative hypothesis. We're going to draw the bell curve and then make a conclusion since we already know the test statistic. I'm going to write down the critical value in a second. But all we're doing is practicing a conclusion. In future examples, we're actually going to calculate the test statistic. So, I am looking here, we are testing the claim that the mean pulse rates for men is more than 74. So my claim is that the mean is greater than 74. Remember when we were writing our null and our alternative, the null is always that the population parameter is equal to that value, and the alternative in this case is going to be greater than, because that's what we're testing. We're testing that the mean is greater than 74. We have a sample of 30 men, that's great. We found our X bar to be 78, and we found our S to be 32, or excuse me, our standard deviation to be 3.2, so S is equal to 3.2. We now, in this case, have a level of significance of 0.05. Let's write the null and alternative. We did that. Draw the bell curve. And what type of test is this? Well, we have our bell curve. 74, we're assuming, is in the middle of our sampling distribution. This is a right-tailed test because we are dealing with a greater than. So here is going to be our rejection region. Our rejection region is going to have an area of alpha, which is 0.05. If I were to look up the critical value, in other words, what value here, the critical value, is going to be a t-score with 0.05 to the right and a certain number of degrees of freedom, 1 minus our sample size, so 29 degrees of freedom. If I look that value up, a t-score with 0.05 in one tail, we're just looking at one tail, and 29 degrees of freedom, so 29 degrees of freedom with 0.05 in one tail, it's entirely in this tail, is going to be, let's see, 1.699. That is the critical value. The critical value, 1.699. In other words, if we calculate a test statistic, and that test statistic lies further away than 1.699, then it's going to be in this rejection region. We were told that the test statistic was calculated to be 6.85. So 6.85 is definitely past 1.699 and in this rejection region. So since our test statistic, is greater than our critical value, in other words, our test statistic was 0.85, and that's larger than 1.699. Then what we see here is that this is in the rejection region. It's in the rejection region. What are we going to do then? We are going to reject the null. Reject the null. And when we say the null, reject the null hypothesis, which means there is evidence to support. There is evidence to support the claim that the mean pulse rates of men is larger than 74. And that's essentially what we're doing. If we calculated a test statistic that was 1 point, let's say 4, and not 6.85, but we calculated 1.4. Well, 1.4 doesn't lie in this rejection region. So we would say we fail to reject. We fail to reject the null hypothesis because there's not enough evidence to say that it's significant. What's significant is if our test statistic lies past this critical value, and the critical value is given based on a level of alpha, or significance level. What is significant? Well, in this case was 0.05. 1.699 separates the lower 95 from the upper 0.05, so anything that lies to the right of that is going to be significant, which we found 6.85 to lie past that particular value of 1.699. The critical value approach always compares a test statistic and a critical value. If the test statistic is further away or larger in absolute value than the critical value, then we know we're going to reject the null, and we would say there is evidence to support the alternative.